Welcome to my LeetCode Visually Explained series. So, did you guys know that all those thousands of LeetCode questions, almost every single one of those interview problems basically boil down to just a few patterns? They're things like two pointers, sliding window, binary search, trees, and hash tables. Instead of memorizing hundreds of random solutions, if you master these fundamental patterns, you can solve almost any coding question thrown at you. As a matter of fact, most of human intelligence is actually simply just pattern matching. It's not that everyone's insanely smart. We just all are very good at matching patterns and things that we've seen before. So for the first video in the series, we're going to be starting off with pattern number 1, the hash table complement lookup, using the most famous LeetCode question of all time, of course, the two sum. So I'm going to be trying to explain this both as simply as I can and as visually well as I can, so you can kind of begin to understand what's happening inside of your RAM memory when you write code onto your screen. So the first thing I'm going to do is break down what twosome is actually asking us to do. So what is it asking us to do? Well, let's say we're given an array of integers, which an array would all be stored in one continuous block in RAM memory, so all in one long string or block. For example, you can have 3, 7, 11, 15, and a target sum like 10, and our goal is to find the indices of the two numbers in the array that would add up to the target we're looking for. In this case, obviously, it would be 3 and 7, which adds up to 10. But one thing we need to remember is that in Python, our indexes actually start at 0. So it's not going to be index 1 and index 2. What we're actually going to get is index 0 and index 1. Okay, so let's start off with the most intuitive way of solving this question, brute force. So let's say you would ask a random person to solve this question and they didn't overthink it. The most simple thing that they would probably come up with is to take the first number and compare it with every single other number in the array to see, obviously, if it matches up to the target number. In code, this basically means just setting up two nested loops. So our outer loop pointer, first number index, would start at 0, and then our inner loop pointer, scanner index, would start right next to it at index 1. And we just do what we would do in our human brain. We check, does 3 plus 7 equal 10? Yes, so we'd return 0, 1. That was really easy because our answer was right at the beginning. But let's say we have a really large array. And instead of having these two numbers at the beginning of the array, our numbers are a lot more towards the end. Let's say we have a billion numbers in the array. That means you'd have to check one number with a billion other numbers, and this would continue to exponentially grow until basically you don't have enough memory to solve the question you were trying to do in the first place. Okay, so before we actually fix this bottleneck, let me explain how a hash map actually works under the hood. So a hash map, what it is a dictionary in Python, and what it actually does, it allows you to map keys to values for instant lookup. But how does it actually do that? Well, you take your input key and you pass it through a hash function, which is basically just a mathematical operation. It's often done using a prime number to calculate an exact location index in memory. So using a prime number helps avoid hash collisions, which is when two different keys end up trying to map to the same location in memory. In the worst case scenario, if every single key collides the same spot, a hash map would degrade back into an array, a complete slow one-by-one scan. But when you use a good hash function, lookup is now instant O of 1, constant time. So how do we actually use a hash map to solve the two-sum in one single pass? Well, instead of using nested loops to compare every single pair, we need to change the question that we've been asking. As we step through the array one number at a time, we don't scan ahead. We literally just ask, what exact number do I need to reach my target sum? And this is where the formula comes in. Needed complement is equal to target sum minus current number. At every single element, we do two quick steps. First, we check our hash map to see if our needed complement is already in there. And if it's not, we store the current number and its index in the map. And then we move on to the next number. And because the hash map lookups table is instant constant time, this single pass solves the entire problem in one single pass. All right, so let me show you how this works step by step on screen with the array, let's say 3, 11, 15, and 7, with a target sum of 10. So for step 1, at index 0, we need 10 minus 3, which is obviously 7. Is 7 in our map? No, it's empty, so we store key 3 at index 0 on the right. Then for step 2, we move to index 1, which has a value of 11. We need 10 minus 11, which is negative 1. Is negative 1 in our map? Nope. So we store key 11 at index 1. Then we move on to step number 3, index 2, which has a value of 15. We need 10 minus 15 is negative 5. Is negative 5 in our map? Still no. So we store key 15 at index 2. Then we move on to step 4, index 3, which has a value of 7. We need 10 minus 7, which is 3. Is 3 on our map? Yep, it was right at the beginning from index 0. Boom, in a single pass, our hash map built memory all the way to the end, caught the match at index 3, and returned index 0 and index 3. And because hash map lookups take constant O of 1 time, our overall runtime drops from a crawling O of n squared to a lightning speed O of n. Okay, so let's take what we visualized and actually translate it into Python code. So before we begin, one thing I would like to, encourage everyone watching this to do is create very clean variable names when you create your code. This is so that you yourself and anyone else in the future will really understand what's happening behind the scenes and what your original intention was when creating the code. It also makes debugging a lot easier when you sit down and, create meaningful variable names to the code that you're trying to make. And it sticks in your brain a lot better too. All right, so to begin our code, we first take and create our solution class with our toSum function. It takes self, our input numbers list, which expects a list of integers, and target sum, which expects an integer target. And it promises to return a list of integer indices. All right, so for line 1, we declare an empty hash map called num to index map. This dictionary is going to map every single number we see to its index in memory. All right, next, we set up a for loop using Python's enumerate function. Enumerate goes through our array element by element, giving us both the current index and the current number at the exact same time. Inside of the loop, step 3, we calculate our missing piece. Needed complement is equal to target sum minus current number. All right, step 4, we check if needed complement in num to index map. If our complement, is already in the map, we grab its stored location using previous index equal to num to index map, needed complement, and immediately return previous index comma, current index. That returns our answer and exits the code. If it's not in the map yet, step 5, we store num to index, current number is equal to current index, saving our number and index into memory, and keep moving. Look at how clean and readable that code is. Just a single pass with instant O1 lookups. Throughout this video, I've explained the two-sum problem to you guys, both visually and in code. But the main thing I want you guys to come away from this video is not to memorize the code or every little bit of syntax, but rather to memorize the core concept explained in the beginning of the video, the hash map. This is a massive pattern that comes up again and again in technical interview questions. Whether they ask you to find a target sum or a target number, it's a great idea to build a hash map so you can trade that memory space and eliminate that nested loop bottleneck, you know? Hopefully this visual breakdown helped you to understand what's really going on behind the scenes in memory. When I sat down and thought about what's happening visually, it really helped me a lot, and I'm hoping that I can do the same for you. Simplifying these ideas so it's not just all syntax, but rather, you know, the fundamental concepts and patterns that you're going to see again and again over and over in coding. Well, thanks for watching, and I hope to see you guys in the next LeetCode video, and I'll catch you guys next time.